A car traveling at 25 meters or miles per hour is to stop on a 35 meter long shoulder of the road. What is required? What is the required magnitude of the minimum acceleration? How much time will elapse during this minimum deceleration until the car stops? So the first thing we want to do is we want to draw a picture and gather some information and then select an equation that'll help us find the unknown variable. So for every physics problem, usually what you do is you list the knowns, what do you know, then you draw a picture to kind of wrap your mind around it, and those two steps, it doesn't matter which step comes first, but those are the first two before you proceed. So list what you know, draw a picture, and then you're going to find an equation to help you find what you don't know, right? And so let's do that. Problem number 39 says that a car is already in motion. Okay, so here's my car. And its velocity is 25 miles per hour. Okay. And its initial position, even though they didn't give it to us, we can arbitrarily make that 0, right? Because we can start 0 wherever we want. Well, it says that it has to stop within 35 meters. So our final position then would be 35 meters further down the road. Okay. And then it says, what is the magnitude of the minimum acceleration? So think about this. The car is in motion this way, and we want to slow the car down. So we're going to start thinking about vectors and magnitude and things of that nature. In order for the car to slow down, if the velocity is in the positive direction, think of this as a number line where this direction is positive and this direction is negative, then we would expect our acceleration, which is going to slow down the car, to be a negative value. I don't know what it is yet, but I know that it's a negative value because the acceleration has to oppose the velocity. So, how do I find that? Well, there's a couple of things we could do. It doesn't tell us how much time would elapse, it just wants to know the acceleration. So here, what we need to do is go through our kinematic equations and pick out which one will be helpful to us. So again, in our textbook, if we go to page 57, and I'm not even going to say what they are. I'm only going to list the ones, though, that have acceleration. So we have final velocity is equal to the initial velocity plus the acceleration times time. We have initial position, or I'm sorry, final position is equal to the initial position plus 1/2 times the velocity plus the initial velocity times time. We have this one here. I mean, you guys know what it is. I don't have to say it. I get confused talking and writing at the same time. Okay. And then lastly, we have V naught. Now, if I were in high school and I saw those 4 equations and I had to pick the one that'll help me get the answer to this problem, and I didn't draw the picture and I didn't list all those things, I'd be frustrated too. But let's look at this. It's asking for the acceleration, but I don't have the time. It's probably not that one. Probably not. Okay. Next one. Doesn't even have acceleration in the equation. Probably not going to use that one. This one looks nice, but it doesn't have the time. I don't have the time. Okay. Huh. This one looks good because it has acceleration and it has the displacement, and I have those. I have the initial velocity. The only problem with this is I'm not quite sure what the final velocity is. Or am I? Let's think this through. My car is traveling at 25 miles per hour. I have to come to a complete stop in 35 meters. Well, a complete stop would mean that my velocity would have to be 0 meters per second, wouldn't it? So this is the one. This is the one that will work. I just gotta, before I could crank through all the math, I gotta convert this 25 miles per hour to meters per second. So let's do that first. I'm gonna say V naught is equal to 25 miles per 1 hour. And we know that 1,609 meters is equal to 1 mile. We also know that 1 hour is equal to 3,600 seconds. Miles cancels with miles, hours cancels with hours, and I'm left with meters per second. Okay, so let's crank through the math and see what we get. So I'm going to pull up my calculator, and I'm going to say 25 times 1,609, and then I'm going to take that number and divide it by 3,600. Cool. So my initial velocity is actually 11.17 meters per second. So I can plug all this in. If I take this equation, I get 0 meters per second is equal to 11.17 meters per second. I'll write it like this, it'll be easier for me. Plus 2 times the acceleration, which I don't know what it is, times the displacement, which is really 35 meters, right? Okay, so now I probably should, yeah, right, because 35 minus 0 is just 35, right? So now I've got to solve for A. So what I'm going to do is I'm going to move some stuff around, and the next step I'm going to say 11.17 meters per 1 second is equal to 2 times 35 meters times A. Okay, so then in the next step I've got 11.17 meters per second is equal to 70 meters times the acceleration. I made a mistake. Do you guys see what my mistake is? My mistake is that if I divide by 70 meters on both sides, okay, I get 11.17 meters over 70 meters second. That's my acceleration. Now, if I did not write my units, I would not catch my error. My final answer should be meters per second squared because that's the unit measure for acceleration. So somehow I made a mistake. Let's go back and look. The mistake that I made, and I want to say that I did it on purpose to teach you guys a lesson, but I just made an honest mistake, is that the original equation was this velocity squared is set equal to this velocity squared. But when I plugged it in, I forgot to square my velocities. So what we're going to do now is we're going to make sure that we square them. However, 0 squared is still 0, right? But what it does is it changes these units. It becomes 0 meters squared over seconds squared is equal to whatever 11.17 is squared, which is 124.85. That's going to be meters squared over seconds squared. See how that works? okay, plus 2 times 35 is 70 meters times the acceleration. Okay, so now when I move this over to the other side, okay, now when I move this over to the other side, I get negative 124.85, and I forgot the minus sign too. Boy, I'm not doing so good. Per second squared, right, is equal to 70 meters times the acceleration. Now when I divide both sides by 70 meters, look what happens. One of these meters cancels with this meter, and I've got 124 divided by 70. And now I get a pretty good answer. Negative 1.78 meters per second squared, and that's my acceleration. Okay, it's a pretty common mistake actually to forget to square that. And then the other thing is that when I moved this over to the other side, I forgot that negative sign the first time. So now, with confidence, I could be pretty sure that I have the right answer. And I just looked, and that was the correct answer. So what am I saying? I'm saying that if I'm in a car that's going 25 miles an hour and I have to stop in 35 meters, if I choose to accelerate at negative 1.78 meters per second squared, I'll be able to stop in exactly 35 meters. So that's pretty much it. Now, one thing, there's a couple of things that Mr. Adams did to double check his work. The unit analysis or the dimensional analysis was key in me catching my mistake. I forgot to square things. When I forgot to square things, I didn't end up with the proper dimensions, meters per second squared, right? So that was a clue that I had the wrong answer. I mathematically had a number, but the dimensions didn't match up. Because Mr. Adams wrote in his units and followed it through algebraically, I picked up on that. I picked up the other mistake of the negative sign because I thought about the problem from the beginning. If my car is traveling this way and I'm slowing down, then my acceleration has to go in the opposite direction. So we think of this kind of like a number line, but really the car is traveling in a positive direction while the acceleration has to be in a negative direction, causing the car to slow down to get to the 0 meters per second. That's it.